This will be a talk about DMFT, but I think somewhat different than most of the applications that are discussed within this workshop, in that it will not be about solving the electronic structure problem of strongly correlated fermions, but it will be purely a application to trying to understand the properties of phonons in crystals. So the work I'll talk about today was done by two fantastic people in my group, Petra, a student, and Dipti, a postdoc. So just to make sure we're all on the same page, because again, this will not be really an electronic structure talk. This is a talk concerned with the properties of phonons in crystals. So working purely in the Born-Oppenheimer approximation, I'm going to imagine I have the exact solution to the electronic structure problem for the ground state. And then I imagine that that ground state defines a potential energy surface on which the dynamics of nuclei evolve. So I have a vibrational Hamiltonian. This is the kinetic energy of all of the nuclei and some many-body potential energy surface. The standard approximation is to diagonalize the Hessian, the matrix of second derivatives of the potential energy surface. That defines phonons in crystals. So within that harmonic approximation, I have a kinetic energy for my phonons. I have phonon frequencies and phonon displacements. But again, the true potential energy surface is a essentially n-body quantity. And so the residual, the remainder of the potential energy surface, defines all of the anharmonicity. And you can think of those anharmonicities as being interactions between phonons. So for example, at lowest order, I could have 3 phonon scattering. I have some interaction vertex, which is like a third derivative of the potential, and then a product of 3 displacements for these phonons. Why should we care about phonon anharmonicity? It's responsible for many of the interesting properties of crystals. So for example, it's responsible for the temperature dependence to shifts in phonon frequencies. So this is things like phonon hardening and softening. It's responsible for the temperature dependence of the lifetime of phonons. So I might care both what is the lifetime of phonons generically, but if I ever want to do a calculation of the thermal conductivity, I require phonon lifetimes, otherwise it's undefined. And even the stability of different crystal structures and the temperature dependence of that is dictated by phonon anharmonicity. So of course, as many of the electronic structure people know, many times you'll do a calculation of a crystal of interest and find imaginary frequencies. And this is largely a product of the fact that you're not including phonon anharmonicity at finite temperature. So how can one include anharmonicity in a computational framework? I'd say there's 2 main methods. One is you can try to just do direct simulation of the dynamics of the nuclei. So if you're satisfied with the classical approximation of the nuclei, then you can do this by molecular dynamics. So again, for the purpose of this talk, I'm going to completely ignore where the potential energy surface comes from. But I could imagine, say, doing density functional theory to provide a reasonably accurate set of forces. I can evolve the nuclei and do classical molecular dynamics. And that is an exact treatment of anharmonicity to all orders. But that can be quite expensive. I usually have to go to long time scales. I have to use large supercells. And how I include nuclear quantum effects is very hard in that framework. There are approximate methods, mostly based on path integrals, but I won't talk about that today. The alternative would be some kind of many-body theory. And I think within sort of computational material science, this is probably the standard. So one can do various treatments of anharmonicity within mean field theory. This is maybe things like self-consistent phonons, if people are familiar with that technique. That, of course, still just provides a static mean field picture. And so the standard thing is then to do perturbation theory in order to calculate things like phonon lifetimes. But as this audience knows extremely well, approaches like this are typically only applicable when the interactions are weak. So for phonons, that means weak anharmonicity. And so, of course, today will be about an effort to use dynamical mean field theory to treat this problem. So the object of interest for our DMFT is the phonon Green's function. So that's the Fourier transform of a time correlation function of the phonon displacement operator. So that will be my U throughout this talk. But you can think of this as like A dagger plus A, if that's more useful. And in sort of a textbook sense, the phonon Green's function has the form I show here. So it's the inverse of some difference between the frequency and the square of phonon frequencies. And then, as usual, I'll have a term that accounts for all of the phonon-phonon interactions, and that will be the phonon self-energy. And again, following sort of textbook notation, my phonon self-energy will be indicated by pi. It's a temperature-dependent quantity, and its job, of course, is to get all of the frequency shift and lifetime information correct. Just to have sort of a cartoon picture in your head as we go through the talk, here's an example for what would be the spectral function of strontium titanate for its phonon band structure. Again, not its electronic band structure. So in the dashed lines, I might have some mean field or quasi-particle picture of the phonon band structure. But because those phonons interact with one another, in reality, they might have frequency shifts or finite lifetimes, as indicated by the line widths that you can see in a typical spectral function. So our goal is to be able to calculate properties like this one, especially for systems for which the anharmonicity might be quite strong. And so just like for the electronic structure problem, the DMFT in this talk is going to be a non-perturbative approximation to the phonon self-energy. And it will be a local approximation. And so it's going to be neglecting all of the long-range anharmonicity by neglecting the momentum dependence to the phonon self-energy. Okay, so as a sort of cartoon picture of what this looks like, here I have a crystal of atoms. They are interacting with one another, and oftentimes we think of that as being atoms connected by springs. As usual, I will recognize that in a periodic system, I can sort of arbitrarily partition and make one unit cell special. I call it my system. The rest of the unit cells in the crystal will then define a bath. And again, just like for the electronic structure problem, I can exactly produce within a harmonic approximation a single unit cell, and the atoms of that unit cell are coupled to a bath of harmonic oscillators, so not a bath of free fermions, but coupled to a very special bath of harmonic oscillators, for which within the harmonic approximation, I can make the properties of these two things agree exactly. But then I'm going to use that bath of harmonic oscillators that reproduces harmonic properties exactly, and I'm going to reintroduce the true anharmonicity between the atoms within my unit cell. This will produce some kind of system bath Hamiltonian for vibrational degrees of freedom. So using somewhat schematic notation, I'll have a system part, which is the kinetic energy of all of the nuclei inside of my unit cell, and the fully anharmonic local potential energy surface. Then I'll have a bath of harmonic oscillators and bilinear coupling between the displacements of the atoms inside of my unit cell and the displacements of all of these fictitious harmonic oscillators. That's a Hamiltonian that's much more tractable than the full crystal one. And of course, it can be solved now using some kind of impurity solver. So it can absolutely be solved using quantum dynamics, and I'll talk very briefly about that today. But one thing that I think is quite neat is that it can also be solved in a fully classical approximation. So if I don't think that nuclear quantum effects are important, which for many crystals is a very good approximation, then I can solve the dynamics of the atoms belonging to the unit cell as the solution of a generalized Langevin equation. I have a fully anharmonic set of forces on the atoms within the unit cell. I have a friction, but that friction has memory, and there's a random force, and these two have to satisfy detailed bounds. So I can solve this generalized Langevin equation, where again, the friction is really taking account of the interactions between the atoms in the unit cell and the atoms in the rest of my crystal. I can calculate an impurity Green's function, and from that, I can extract the local approximation to the phonon self-energy. So back to the cartoon, I use this local phonon self-energy to update my description of the lattice problem for the full crystal. And I can think of the phonon self-energy as kind of being the introduction of frequency-dependent spring constants between all of my atoms, if you like. But again, within that approximation now, again, as this community knows, I can update my description of the bath of harmonic oscillators or hybridization or spectral density. That will define a new impurity problem. I have to solve that impurity problem once again, and this process can now be iterated to self-consistency. So that's the idea behind this vibrational approach to DMFT. And again, it can be done fully within the context of doing classical nuclear dynamics given some potential energy surface. So I'll show you, for the rest of the talk, I'll show a little bit of results on model systems, just sort of establishing the accuracy of dynamical mean field theory for phonons, and more recent applications to realistic materials. So this is just a one-dimensional model of optical phonons. So I'll have a Hamiltonian, and on this 1D lattice, I have the kinetic energy of all of my atoms. The atoms will be connected by springs. And then each atom is also going to feel a local potential. And that local potential here will be chosen to be quartic. So this...
Tim, just sorry to interrupt. Just to, before we switch to examples, so just to be on the same page. So the self-consistency condition requires that the local Green's function of your embedded problem is equal to the full phonon Green's function Q subbed, right? And same for the pi over omega. Okay.
Yep.
I see.
Exactly right.
Okay, thank you.
For whatever it's worth, we find that for many problems within application of phonons, that self-consistency converges relatively quickly. So only a few iterations is typically good enough. But otherwise, yeah, the self-consistency condition is exactly the same as for electrons. Yeah, so this will be the model. Atoms connected by springs with a local quartic potential. And because this local quartic potential breaks infinitesimal translational invariance, the spectrum of this Hamiltonian will have a gap. So that's why this is a good model for optical phonons. And so I can just simulate this within the classical nuclear approximation by doing molecular dynamics. That's relatively straightforward. And if I do that, I get a phonon band structure for this single band that looks like this. Within a purely harmonic approximation where I neglect this quartic anharmonicity, I have the dispersion of some optical phonon. And then if I simulate this exactly by molecular dynamics, there's a shift to higher frequencies. So that's commonly called phonon hardening because of the quartic anharmonicity. And clearly there's a line width associated with a phonon lifetime. And if I just do single site dynamical mean field theory for this problem, this is the spectral function that I get. And you can see that basically to graphical accuracy, it's almost identical to molecular dynamics. And again, just as a reminder, what is being done is that this lattice problem of atoms connected by springs with local quartic pinning potentials is just a single atom inside an anharmonic potential coupled to a very special bath of harmonic oscillators. And it's the job of that bath of harmonic oscillators to mimic the rest of the lattice. And all I have to do is solve this generalized Langevin equation for that single degree of freedom. So in a computational sense, the results on the left were generated by doing molecular dynamics of 200 coupled anharmonic oscillators, whereas the results here in the middle are molecular dynamics of just a single anharmonic oscillator with a very special bath of harmonic oscillators. And although I won't really go into details, there's sort of an interesting observation, very much like with quantum impurity solvers, where I can either choose to discretize this bath of harmonic oscillators and simulate their dynamics explicitly, or I can just try to solve this generalized Langevin equation directly, and all I need to know is the functional form of this memory kernel. Here's just the vibrational density of states. So what I get by summing over the momentum of this phonon spectral function. And in gray is the harmonic vibrational density of states, which, as people might know, for phonons in the harmonic approximation, it's temperature independent. So I get no information by changing temperature. Whereas in the colored symbols, I show the results from DMFT. And if you can see it, there's also a thin line showing the exact molecular dynamics results. And they're basically right on top of each other for all temperatures, and consistent with what one expects for these quartic potentials. As I increase the temperature, the phonon frequency shifts to higher frequencies, and I have a larger line width consistent with a shorter lifetime for this optical phonon mode. So like I said, everything here has been with classical dynamics. You can ask, could we do quantum dynamics? And for this model problem, the answer is yes. So again, I won't go into details. I'm happy to chat about it if people are curious. But as a reminder, the impurity problem here is just a single anharmonic oscillator coupled to a bath of harmonic oscillators. And using DVR type methods, one can simulate the dynamics of that, quantum dynamics of that exactly. So if I do that, I get the spectral function on the right at the same temperature. And perhaps unsurprisingly, it is different than the classical approximation. So basically, given the parameters that were used for this model, it's not good to treat the nuclei fully classically. I get a much more structured spectral density when I include nuclear quantum effects. And here again is now the vibrational density of states, what I get by summing over the momentum. Where again, I have the harmonic one on the left, which is identical whether I use classical or quantum mechanics. And then in yellow, orange, red are increasing temperatures, comparing the quantum vibrational density of states to the classical vibrational density of states. And again, consistent with one's expectations, at lower temperature, you see more structure in the quantum one, and it disagrees more with a rather smooth classical density of states. But as I increase the temperature, they start to agree with one another, which is, of course, when I expect quantum and classical dynamics to agree. So that's all I'm going to say in this talk about nuclear quantum dynamics. But again, if people are interested in that, I'm happy to chat about it more, say during Q&A. And in a sort of provocative statement, I'll say, if you believe the accuracy of the classical dynamics result, namely that single site dynamical mean field theory with classical nuclear dynamics gives basically exact agreement with full anharmonic classical molecular dynamics of an entire lattice. If you extrapolate that agreement to the quantum case, then our argument is that perhaps these results are essentially numerically exact finite temperature nuclear quantum dynamics of a solid. But that's much harder to validate, of course, because solving the nuclear quantum dynamics of the full lattice problem is borderline intractable. Okay, so with that model demonstration finished, I'm going to proceed to an application to real material. So the material that we'll be applying DMFT to is this class of Clathrate solids. So the unit cell is shown here. And there's basically a Clathrate framework made of gallium and germanium atoms. So that makes sort of the spheres that you see here that make this framework. And then inside of this framework of sort of spherical cages, one can place guest atoms inside of these Clathrates. So these guest atoms X for this gallium germanium version are commonly barium or strontium. And again, they live inside of these Clathrate cages. So this class of materials is of interest to many people because they are promising thermoelectrics. The figure of merit for thermoelectrics is inversely proportional to the thermal conductivity. So a good thermoelectric should be a very poor conductor of heat. And in roughly an intuitive or hand-waving sense, these materials do have low thermal conductivity that's attributed to the rattling of these guest atoms inside of these Clathrate cages. So again, they're essentially very loosely bound. They don't really form covalent bonds to any of the atoms in the clathrate. And so they just rattle around inside of these cages. And it's believed that that rattling is responsible for their low thermal conductivity. So unsurprisingly, we're interested in understanding those dynamics from the perspective of dynamical mean field theory. So here's the phonon band structure of a model of this material where I remove all of the guest atoms. So this is basically the empty clathrate. And you can see there along this particular path in the Brillouin zone, there are acoustic phonons. And as I imagine people are familiar with, the acoustic phonons are primarily the ones responsible for contributing to the thermal conductivity. But when I introduce these guest atoms inside of the clathrate cages, this is how the phonon band structure changes. I basically get some new, very flat optical phonon modes. And in particular, because these guest atoms almost rattle freely, they can be very low frequency. And so down here, there's a relatively low frequency, flat optical phonon mode that essentially cuts through the dispersion of the acoustic phonons. And so again, this is a rough understanding of why that might lower the conductivity of the material and thus make it a good thermoelectric. But all of this is, of course, within the harmonic approximation because I'm just showing you phonon band structures. So I won't go into any of the details, but we've simulated a model of this system using dynamical mean field theory. So here's the phonon spectral function of the barium version at room temperature. And in the dotted lines are the harmonic phonon band structure. And then as a color map is the DMFT phonon spectral function. You can see the agreement is pretty good. At least the location of the phonon bands is reasonably well reproduced in the harmonic approximation. But there are some slight shifts, and there are lifetimes to the phonon modes, of course. For this model, one can do the work and try to do explicit molecular dynamics simulation to extract a spectral function for comparison. So this is much more expensive, so we don't quite get the same resolution through the Brillouin zone by explicit MD. But what we get is shown here on the right. And you can see, again, the agreement is pretty good. We just get much better resolution from dynamical mean field theory. Again, for the experts, of which many of you are, because you have access basically to a self-energy that you can apply to the entire lattice Green's function, it's very easy to generate smooth spectra from DMFT. And again, now from a computational point of view, the difference here on the right, this is doing explicit molecular dynamics of more than 8,000 atoms. And that's the supercell size that we need just to get this kind of resolution throughout the Brillouin zone. Whereas on the left, this is just a single unit cell. So it's single site DMFT in that sense. So I'm just doing MD of something like 8 atoms plus a special bath of harmonic oscillators that introduces a sort of memory dependent friction to their dynamics.
So Tim, if we compare the computational costs of these two simulations, what does that give?
It's much cheaper to do the one on the left. So it's a
and how much is much?
I can't give you an exact number, but I can give you the more qualitative statement, which is, I think, the relevant one. It's interesting to compare within the classical dynamics approximation, phonons versus electrons. So of course, the savings that you have for quantum problems or for fermion problems is essentially exponential, right? In going from the full lattice problem to just a single unit cell, I essentially have savings that's exponential in that difference. Here, the cost of doing exact classical molecular dynamics can be as cheap as n squared, where n's the number of atoms, if I just have sort of relatively simple things like pairwise interactions. If I'm using electronic structure to generate forces, then doing a single time step of molecular dynamics is whatever is the cost of the electronic structure. So that could become something like n cubed if I was using density functional theory to calculate forces. But roughly in your head, you can imagine that it's the sort of ratio of system sizes, 8,000 over 8, raised to a polynomial power of 2 or 3. So I'd say that's why it's a little bit different than DMFT in that electronic or quantum versions of DMFT, where you're taking a problem that would be truly intractable and making it tractable. Here you're taking a problem that is probably tractable, but it would take a very long time, and now making it very, very fast.
Hey, Tim, can I ask a question?
Yeah, of course, Miguel.
So whatever you just said is, I completely agree, except that if you want quantum dynamics, that is not true anymore, right? Because for quantum dynamics, we don't have any way really to get. So if you want quantum anharmonic effects on like Raman spectra or anything like that, we don't have any tools.
100% agree. So I'd say the state of the art right now would probably be some kind of path integral molecular dynamics technique. So this would be things like ring polymer molecular dynamics.
I mean, but they all break down near room temperature, right? So technically, if you want anything, few hundred Kelvin, even centroid or RPMD, none of these things really work well.
Absolutely agree. Yep. Right. Anytime you want true quantum coherence, we have close to no techniques. And I won't talk about it in this talk. For people who want to chat with me later, we're doing other work in the group to calculate quantum spectral functions for relatively large numbers of degrees of freedom that could be used as an impurity solver. And how we're doing that is, again, something I'm happy to chat with people about. But exactly like you're saying, Miguel, that's an approach that is, conceivable within the DMFT approximation, where all I need to do is treat the number of degrees of freedom in a unit cell, whereas we will never be able to apply those techniques to the full lattice to converge the problem.
Can I ask a quick question about your previous slide, or maybe 2 slides ago, when you showed that introducing those rattler atoms changed the acoustic phonons enough to change the conductivity? I didn't really catch it, because looking at the pictures, the acoustic phonons looked pretty unaffected. I didn't really understand that comment.
So one of them looks unaffected and the other one is affected. So the lower one here indeed looks relatively unaffected. This one here is the one that really gets cut by this particular placement.
I see. It's not the low end of the branch. You actually are interested in the zone boundary kind of end of the acoustic phonons.
Yes. And of course, the lower the frequency of this guest mode, the sort of lower in frequency it's going to cut into this acoustic phonon. And I'll show you an example.
That's fine. No, I got that. It's just I was mostly focusing on the low end, the low end. Okay, thanks.
Yep, no problem. So I'll more or less show exactly an example that gets to Vadim's question right now. Like I said, you can change the guest atom from barium to another material like strontium. And here this is the potential energy as calculated by density functional theory of what happens if I move the guest atom inside of its clathrate. And so the potential that's traced out for barium is shown here in blue. The potential that's traced out for strontium is shown in orange. So you can see it's much lower frequency. It's flatter near its minimum. And its anharmonicity is stronger. So it's the quartic part of it is much stronger than it is for barium.
Excuse me a second, Tim.
Yeah.
Just I, at least, and probably others, don't see anything on Zoom. Or do you intend for people to see what you're talking about?
Yes.
We do see a slide.
So does everybody else see? Because the screen is, oh, I see. All right, never mind. I'm sorry, the Zoom has 2 windows. Now I see. You were sharing before, and now, anyway, sorry for the interruption. Okay.
That would have been a rough talk if I didn't see anything this whole time.
Previously, I thought that's what confused me. Anyway, sorry.
Yes, strontium is much flatter, so it will be lower frequency and more anharmonic. And skipping over details and just jumping to the results, here's now the comparison between the molecular dynamics spectral function with strontium as the guest atom and DMFT on the left. Again, qualitatively, you can see that the agreement is extremely good. even though this is still a single site DMFT. And now if you compare this rattling mode that Vadim was asking about, I think maybe now it's even more clear. So it's gotten much lower in frequency. So it now cuts through the acoustic phonons sort of, I don't know, halfway to the zone edge. And in the presence of anharmonicity, you can see now that there is a very large line width to this flat rattler band, and it has a very short lifetime. So to make that comparison a little bit more quantitative, I'll show the spectral function at the X point. So in the dashed line is the harmonic spectral function with just a fictitious broadening added so that you can see it. And things kind of agree at higher frequencies, but at lower frequencies, you can see that this flat rattling mode has been shifted up in frequency quite a lot, from something like 15 wave numbers to 30 wave numbers. And it has acquired a very large line width and thus a short lifetime. So in fact, its lifetime is less than about a picosecond, which is an extremely short phonon lifetime. And so obviously that's entirely due to the presence of strong anharmonicity of these rattling atoms inside of their Clathrate cages. And the agreement between DMFT and molecular dynamics here, again, is essentially quantitative. And the last bit I'll talk about before wrapping up is the ability now to calculate thermal properties or transport properties. So again, for those who do this with electrons for the electrical conductivity, it looks very similar. So the thermal conductivity will be the zero frequency limit of some response function. And that response function is related to the current time correlation function. So for phonon problems or for nuclear degrees of freedom, the current operator has a couple of components. The phonon frequency itself, something like the velocity of phonons or the slope of the phonon dispersion relation. So of course, this is like the speed of sound for the acoustic phonons. And then it's the product of the phonon displacements and the phonon momentum. So you can think of this as saying it's kind of like a two-body quantity. And so now if I want to calculate the current correlation function, I would have to do correlation functions that are like displacement, momentum. And within DMFT, as I've described it to you, we don't get access to two particle type correlation functions like that one. So we do the standard thing and we neglect vertex approximations, neglect vertex corrections for this response function. So with all of those details swept under the rug, here's a plot for the thermal conductivity comparing dynamical mean field theory and perturbation theory, which is the sort of standard approach to calculate the phonon lifetimes that one needs to calculate conductivities. So first, I'm showing you results for the empty Clathrate. Here, there's essentially no anharmonicity, so the conductivity is quite high for these materials. The circles are perturbation theory, triangles are DMFT, and the dashed line is really just a guide to the eye. And it's actually, perhaps ironically, hard for us to converge the DMFT results for materials that have extremely low anharmonicity. So for things that have very high conductivities, just for relatively boring numerical reasons. But if I show you the filled Clathrates filled with either barium or strontium, I get the conductivities that I show here. So green is barium, red is strontium. And again, the circles up here are the results from perturbation theory, whereas the triangles down here are what you get from dynamical mean field theory. So there's something like a factor of 10 difference in the conductivity, with DMFT predicting a much lower conductivity than one can predict by just doing perturbation theory in the phonon anharmonicity. If I show you just the high temperature results for the thermal conductivity, here the black dots are some experimental results for the barium compounds, which you can see agree probably fortuitously well with the green triangles, the DMFT result. And what's kind of interesting is within perturbation theory, the thermal conductivity at high temperature is easily shown to be 1 over temperature. Whereas if we fit the DMFT, especially for the strontium compounds, we see a weaker scaling. It's something like -0.6 in the temperature. So this is relatively new data, so we're interested in this and trying to explain it. I won't go into the details of this data, but we can easily go in and sort of analyze the contributions to the conductivity throughout the Brillouin zone. So we can make plots like this one. This is the phonon band structure, and the coloring on these symbols tells you what is the contribution to the conductivity from a phonon mode at that frequency and wave vector. So when the colors are light, like down here, these modes make a large contribution to the conductivity. Because this optical phonon cuts through them, you see that there's a decrease in their contribution to the conductivity near that rattling mode. And so we can sort of start to try to provide microscopic insight into what's going on as contributions to the conductivity. And in a sort of cartoon picture, which maybe people know from something like relaxation time approximation or Boltzmann transport equation, the thermal conductivity basically has contributions from the heat capacity of a given mode, the group velocity of that mode, and the lifetime of that mode. And so we find within DMFT that it's mostly the lifetime that affects interesting behavior in the thermal conductivity. And so in particular for that strontium-filled Clathrate, if I show you the lifetime of the acoustic modes as a function of temperature, this should be 1 over temperature in perturbation theory. We see that it's indeed 1 over temperature at low temperature, but it sort of flattens to something quite different at high temperature. So this has flavors of resistivity saturation that this community knows well. And this, again, is very, very recent data. So we're sort of trying to understand the implications of this behavior, its origin, and what that means for the high temperature transport behavior of these materials.
What's the Debye temperature of these materials?
I don't know, whatever is 40 or 50 wave numbers converted into Kelvin.
Okay.
I don't know, roughly 50-ish Kelvin is my rough guess. Somewhere between 50 and 100 Kelvin.
I see. So this is the high temperature regime.
So this is definitely high temperature, indeed. Yep, exactly. This is above the Debye temperature. Okay, so let me just wrap up. I've told you, hopefully, that vibrational DMFT is a neat method. It has many of the properties we know from fermionic DMFT. It's exact in both the harmonic limit and in the sort of molecular limit where unit cells do not talk to one another. It's non-perturbative in the local anharmonicity. And in principle, it's applicable to both classical and quantum nuclear dynamics. I didn't have time today to talk about some other interesting things. We've shown that it is indeed systematically improvable by just doing cluster dynamical mean field theory. That works quite well in everything we've tested so far. It can be combined with a more accurate low-level Green's function as sort of the lattice Green's function. So that would be something like doing Hartree-Fock plus DMFT for fermions. So we can do basically self-consistent phonon plus DMFT. And with that, let me again thank my student Petra, my postdoc Dipti. The work I talked about today is in the papers that I show you here. Thanks for questions so far, and I'd be happy to answer any questions that people still have.
Thank you very much, Tim.
For sure. Thanks, Antoine.
So questions? I guess Olivier Gingras, are you monitoring the questions?
So we'll start with Andy.
Hi. Yeah, just great stuff, Tim. Just going back to sort of Vadim's question, the funny temperature dependence of the thermal conductivity. The thermal conductivity you calculate should have a strong temperature dependence when the temperature gets to be lower than the vibration frequency of the Clathrate mode, which is so anharmonic.
Mm-hmm.
Where does that show up? Is that you just didn't access those temperatures yet, or
the low temperature limit?
Well, low compared to that, the frequency of the rattling mode, whatever it is. That's presumably that's the acid test for what's contributing, right?
Yeah, I mean, the data is definitely there. I'd welcome other people's thoughts, but compared to fermions, the low temperature conductivity or low temperature resistivity is a little bit different, in part because there's a contribution to the heat capacity.
Yeah.
So like if you look at the conductivity here, we do see that there's, it's non-monotonic, it has a maximum. And that's basically just saying that at low temperatures, there's a thermal conductivity that is sort of turning on the phonons. And then there's something roughly like 1 over temperature in the lifetime that competes as you go to higher temperature.
Yeah.
So at least empirically, we see roughly 1 over temperature at intermediate temperatures.
Yeah.
But we're still
Right.
looking into
Anyway,
it.
you see what I'm saying? Just that when you get below that rattling frequency, there should be changes both in the scattering rate and or where the rattling frequency crosses the phonon line, both in the scattering rate and in the amount of entropy you have around to play with.
Yes, yeah, I think I agree.
So just it would be interesting maybe to analyze it from your results from that point of view. Anyway, thanks.
I think so too. I mean, we also see just that higher temperature is sort of when anharmonicity is turned on the most, sort of. If you think of it as just like rattling inside of a potential, it's where you are now experiencing the sort of quartic walls of that potential more strongly. But yeah, we can look at the whole regime.
Thank you very much. The next question is from Rob Lavrov.
Yeah, thank you for the talk, Tim. So just thinking in terms of analogs to fermionic DMFT, which is of course not a parameter-free method, can I kind of think of the initial guess for the harmonic bath of oscillators, their frequencies, to be kind of the parameters there, and maybe your version of constrained RPA would be density functional perturbation theory, or some choice of getting the Hessians for those harmonics. And if so, what's kind of the dependency on that? And you mentioned really quick self-consistency convergence, but have you kind of played around with different choices of that?
Yeah, all great questions. So how strongly do I want to wed myself to the statement? In Tianyu's talk next, you'll hear what I'm guessing is a version of electronic DMFT that doesn't have the downfolding aspect, so the CRPA screening element. So I think maybe our approach to DMFT is similar in that formally, if I think about, I don't know, just the Hubbard model or something, I don't have to do a CRPA style downfolding. So that's more for how do I treat lots of bands. So here it's the same thing. We've never tried to basically eliminate any phonon bands. They're all included in all calculations. So there isn't a downfolding type step in the CRPA sense. The bath of harmonic oscillators, indeed, you can think of doing sort of a standard phonon calculation with your favorite method to produce the purely harmonic phonon band structure with DMFT. And then with DFT. And then just by comparing sort of the phonons of a single unit cell with the phonons of my crystal, I can calculate the hybridization function. And if I choose, I can discretize that in some way to make explicit harmonic oscillators. Initial guess, we usually just set the self-energy to 0 as the first go around, and that converges okay within a few iterations. But yeah, also this doing something like self-consistent phonons for anyone who's done that, or temperature-dependent effective potential, or stochastic self-consistent harmonic approximation, other sort of ab initio ways to treat anharmonicity, which requires, of course, ab initio calculation of anharmonic force constants. We can use that as the low-level Green's function as well.
Thanks.
I hope that
and another question, which is less of a mouthful. Your talk on Clathrates made me think of these high temperature, high pressure Clathrate superconductors like lanthanum decahydride. So my question would be, have you thought at all about extending this to electron phonon coupling?
We sure have. Yeah, that's a great question. Yes, so we've thought about both combining it with electrons for problems for which electron phonon coupling is important, and there is reason to think that the phonons are very anharmonic. So short answer, yes. As well as trying to find systems for which nuclear quantum effects are important at the same time as phonon anharmonicity would also be exciting things for us to try to apply this to. which requires the development of these nuclear quantum impurity solvers that I vaguely alluded to.
Thank you.
Yeah, thank you.
Okay, we have time for one last question from Dennis. Those of you who have questions, you can put them in the chat, and I'm sure Tim will look at them.
For sure.
Hey, Tim. I have a very simple question, actually. You show that there's, like, at high temperature, I have my quantum, your quantum solver, it's working pretty similar to the classical one, but below certain temperature, there are deviation. Is this just a Debye temperature? Or what is determining this temperature?
That temperature is something like the optical phonon frequency. That was just a model of optical phonon, so it didn't even have a Debye temperature or a Debye frequency. But yes, basically, I mean, almost the only energy scale on that problem was optical phonon frequency divided by KT.
Okay. And the second this question is, can you give us a rough feeling, how does this Lajoie tails look like? Like this kind of a generalized damping? Is it some very long tails, or in time, or
in time? Yeah, it's relatively long in time. For phonons, it's not too bad. There's an old story in liquid state dynamics that very long, non-exponentially decaying.
So there's some power law.
Yeah, they can be power law for some diffusive dynamics, at least in liquids. I don't know that we've looked into it carefully enough for phonons, but it can indeed be long time for sure.